Hi, today we are looking at our last trig identities, which are our double angle identities. So if these are identities in which an angle is doubled in a trig function, so we've got sine of 2 times our angle is equal to 2 sine of our angle cos of our angle. We also have tan of 2 times our angle is 2 tan of our angle over 1 minus tan squared of our angle. And then we have 3 different cos ones, which depending on the situation, will determine which one we substitute in. So we've got cos squared of our angle minus sine squared of our angle, or 2 cos squared of our angle minus our 1, and then 1 minus 2 sine squared of our angle. And essentially, these bottom two we get by taking this one and substituting our Pythagorean identity in for either cos or sine. So for example, given angle theta is in standard position with its terminal arm in quadrant 4, and cos of that angle is 2 over 5, determine the exact value of each trig ratio. So the first thing I would do is draw out the situation. So we are in quadrant 4, so we know we're down here somewhere. We've got cos is 2 over 5, so that'd be our adjacent is 2 over our hypotenuse of 5. We can use Pythagoras to get this side here. So essentially b squared equals c squared minus a squared, or b is equal to square root of 5 squared minus 2 squared. So it gives us the root of 21. Because it's downwards, it is going to be negative root 21. Now sine 2 theta is equal to 2 sine theta cos theta. So we'll substitute in our ratios for sine and cos now. So we've got 2 times sine of this angle would be our opposite of negative root 21 over our hypotenuse of 5 times cos, which is 2 over 5. So that gives us negative 4 root 21 over 25. Cos 2 theta, we can choose any of the identities. They will all give us the exact same answer. So I'm just choosing the first one. So we've got cos squared theta minus sine squared theta. Now cos, we already said was 2 over 5. So we have 2 over 5 squared minus sine squared. Sine is negative root 21 over 5. And we're squaring that. That's 4 over 25 minus 21 over 25, giving us negative 17 over 25. Okay, next example, write each expression as a single trigonometric ratio and evaluate if possible. So we've got cos squared of pi over 4 minus sine squared of pi over 4. So that matches the identity that we just did. So that's cos of 2 theta. So that's going to be equal to cos of 2 times pi over 4. So that gives us cos of pi over 2, which if we know our graph of cosine, which looks something like this, we know that that's full 2 pi, this would be pi. So pi over 2 is where it crosses our x-axis here. So cos of pi over 2 is 0. Next one, we've got 2 tan pi over 6 over tan squared pi over 6 minus 1. Now this doesn't quite match one of identities. Our denominator is slightly different. So what we can do is factor a negative out of that denominator and move it to the very front of our function. So we've got 2 tan of negative pi over 6. We have that negative in front of everything. Over, factoring negative out will change the signs of these and might as well change order. So we've got 1 minus tan squared of pi over 6. Now this part here, that's does not include that negative in front, now matches one of our trig functions. So that's negative tan of 2 times pi over 6, which is negative tan of pi over 3. Now, if we were to draw out, that pi over 3 would be roughly here. It's one of our angles in a special triangle, so we know this side is square root of 3, this side's 1, this side's 2. Tan is our opposite over adjacent. So we've got negative root 3 over 1, so it equals negative square root of 3. Okay, so next we will do some proofs. So for example, prove each identity. We've got 2 on here. So cotangent theta equals cos 2 theta plus 1 over sine 2 theta. Okay, so looking at this, it looks like this is probably our more complex side. So I'll start with it. So I've got cotangent theta is equal to, I want to replace cos 2 theta with something. Now we've got 3 different options to choose from. So I'm probably going to choose the one that has a negative 1 in it. So that cancels out with this plus 1. So I'm replacing this with 2 cos squared theta minus 1. Then we have the plus 1 over sine 2 theta. If we expand sine 2 theta, that's 2 sine theta cos theta. So if we go through and simplify this, and negative 1 and positive 1 cancel out. This cos will cancel out with one of these. This 2 cancels with this. So that gives us cos theta over sine theta. Now cos theta over sine theta is cotangent theta. So we can say identity proven. Okay, our next example, we have cotangent theta times cosecant 2 theta equals 1 over 2 sine squared theta. So this looks like the more complex side, so I will be starting with it. Cotangent we know is cos theta over sine theta. And then we've got cosecant 2 theta, so that's times 1 over sine of 2 theta, because we know cosecant is 1 over sine. So if we have cosecant of 2 theta, that'd be 1 over sine of 2 theta. So that equals 1 over 2 sine squared theta. So we've got cos theta over sine theta times 1 over sine 2 theta will replace with its identity. So that's 2 sine theta cos theta. And that equals 1 over 2 sine squared theta. Cos cancels out with cos. So we have 1 over 2 sine squared theta equals 1 over 2 sine squared theta. So we can say identity proven. Okay, so next we are doing an example for solving. So we've got 1/2 sine of 2x minus cos squared x equals 0 over to the domain of 0 to 2 pi. So first thing I'm going to do is expand the sine 2x out with its identity. So that gives us 1/2 sine of 2 theta is 2 sine theta cos theta. So we've got 2 sine x cos x. minus cos squared x equals 0. Now, if we have 1/2 times 2, those are going to cancel out. So that gives us sine x times cos x minus cos squared x equals 0. We'll notice that both these terms have cos in it, so we can factor that out. So we've got cos x times sine x minus cos x equals 0. At this point, I'll separate this into two separate equations, because if this equals 0, 0 times anything gives us 0. Same as if this equals 0, that times this will give us 0. So we're looking for where cos x is equal to 0. Now, if we remember our graph of cosine, we start at maximum, and for one period looks like this. One whole period was 2 pi, half was pi. Where it crosses our x-axis was pi over 2 and 3 pi over 2. So we have x is equal to pi over 2 and 3 pi over 2. And now we'll solve this part here. So we've got sine x minus cos x equals 0. I would move the cos x to the other side by adding it to both sides. So that gives us sine x equals cos x. Divide both sides by cos x. Sine x divided by cos x is tan x. So now we're looking for where tan x is equal to 1. Now, if we have tan equals 1, we know that that matches one of our special triangles. We just have to use Castro to figure out which quadrants tan is positive in. So we know that tan is positive here and here. If tan is 1, that means our opposite and adjacent are both 1, which means this angle, that's our reference angle, is going to be pi over 4. So we've got two angles. We've got pi over 4, as well as from here to here would be pi plus pi over 4, which gives us 5 pi over 4. So we have a total of 4 answers. We have pi over 2, 3 pi over 2, pi over 4, and 5 pi over 4.